Hi there, folks. Happy Monday. I woke up this morning thinking to myself, what kind of evil, horrible things can I do today? And this one particular problem comes to mind. But then what happened is I took a nice little run around my neighborhood. I got to pet lots of cute dogs, and then it made me realize that maybe there is enough evil in the world already without my contribution. So I decided for the first time in my life to actually try to be a decent person. So I want to walk you through this particular problem. This is an optimization problem, and I'm just going to say that it took me a really long time to work this one out. I didn't really have to get help from anyone, but I kind of just sat with this problem for a long time, worked on it a number of different ways, and then I was able to get it finally. And that was weird. Sorry about that. I think my mic just disconnected for a second or two. So this is an optimization problem. Let's read through it real quick. A piece of wire measuring 10 meters in length is to be cut into two separate pieces. One piece will be bent into the shape of an equilateral triangle, and then the other piece will be bent into the shape of a square. So we have two parts. Part A, we want to maximize the combined area of the two shapes. And then in part B, we want to minimize the combined area of the two shapes. So as with all optimization problems, it's a really, really good idea to draw a picture of the situation. So we have 10 meters of wire. We are going to cut this up so that we can make all of these shapes with this length. We're going to have just 10 meters. We're not going to have less than 10. We're not going to have more than 10. And that's just kind of the tip off that 10 is going to have to be our constraint. Optimization problems always have a constraint, and that would be the quantity that just cannot change ever under any circumstances. It's always going to be 10 for this length. So what this is going to look like, and bear with me as I embarrass myself to draw this thing for you guys. It's going to look something kind of like this, and I'm going to do my best to preserve the length of the line. It won't be perfect, but by this point, you know not to expect perfection from me when it comes to my drawings. We have a triangle, we have a square, and I know that's not an equilateral triangle. I try to make it look like that, but it just didn't work out. So this is ultimately what this thing is going to look like. The thing is, though, we can vary our parameters a little bit. What I mean by that is we could maybe have something that looks more like this, for instance. We could have a small triangle, and then we can have a bigger square to account for less material being taken up by the triangle. So that's the nature of all optimization problems, is that we can always vary the parameters a little bit to get different outcomes. So we can make the triangle smaller, we can make the square smaller. We're interested in finding minimums and maximums. We're not sure yet what configurations would produce a minimum, which ones will produce a maximum. So we're going to use some calculus to help us get to that conclusion. So let's get started. So we already identified the constraint. We know that the constraint would be the 10 meters of wire we have available for making these shapes. That amount is never going to change. So it's always a good idea to be in the habit of identifying that right away. So I want to put the constraint in English first. So we have 10 meters of wire. This quantity will never change. It's impossible to have more wire or magically somehow have less wire. We're always just going to have 10 meters. It's a fixed amount. So what I want to do now is I want to take the same information and I want to convert it into calculus language, because we can't even begin to solve this problem unless we have a good analytical sense of what this information means in calculus and the tools we need to get us the answer we're looking for. So I wrote down the constraint in English, and we're not even at the calculus stage yet. What I want to do is I just want to write our constraint in algebra language. So we know that we have 10 meters of wire to use. So for example, if we start here and then we work our way all around the figure, that looks like perimeter to me. So it means our perimeter is going to have to be 10 feet. It's going to have to be the perimeter of the triangle plus the perimeter of the square. We don't know the dimensions of either of them yet, so I'm going to use some Greek letter identifiers to help us. So we have alpha is going to be the side length of our equilateral triangle. I think I can make that look a little bit nicer. Alpha. And then I'm going to call beta the length of one side of our square. So we can tell that our perimeter, total perimeter between the two shapes is going to have to be 3 times alpha plus 4 times beta. I'm going to just use P for perimeter, 3 times alpha plus 4 times beta. All right. So now that we have our constraint, we want to identify the quantity that we're trying to optimize. So we're trying to optimize the area. So we're doing part A first. We're trying to maximize the combined area between our two shapes. So just like in the last problem, we want to put this in calculus language as well. But we're going to need some help with that real quick. We're not ready to put that into an equation form. We're going to need to gather our information and create the equation ourselves. So we want to find the area of each of the shapes individually in terms of alpha and in terms of beta. So alpha, we know it's an equilateral triangle. We know that we're going to have side lengths of alpha all the way around. And I think I actually want to draw a bigger triangle to help us understand better. It'll help us, it just makes it a little bit more clear what the dimensions are supposed to be. So this is alpha. We know the area of a triangle is going to be 1/2 base times height. So we have the base already. The base is just going to be one side length, that's alpha. Base is equal to alpha. But now we need to find the height. So I don't know if you have completed trig recently. I don't know if you guys remember the special right triangles, but we're going to need some of that knowledge to help us with this step of the problem. So remember, for a basic 30, 60, 90 degree, 30, 60, 90 triangle, and by the way, we know for sure it is 30, 60, 90, because all equilateral triangles are going to have a 60 on top and 2 base congruent 60-degree angles, which means this right here is going to be 60. This guy right here has to be 30 by extension. We're cutting 60 in half. This is our angle bisector. I know it doesn't look like a perpendicular bisector. That's just because I suck at drawing. It's supposed to be the perpendicular bisector. And then we know, of course, we have a 90 right there. So this is a 30, 60, 90. So in the most simple case of a 30, 60, 90 triangle, we have a height of 3, and we have a base of 1 and a hypotenuse of 2. So we want to adapt this. We want to make some kind of a modification to this to match what we have in our problem. So we have to figure out, well, how do we go from 2 to alpha? So what that means is that we have to multiply by alpha over 2. And then we're going to do that with the other 2 sides as well. We're going to have √3 times alpha over 2. Just to make sure that we keep all the proportions equal. So now we have 1 times alpha over 2. So if we look at the hypotenuse, 2's cancel, we're left with alpha. So our hypotenuse is alpha. Let's just verify and make 100% sure that this is what we want. So we look at this big abomination over here that I drew. We can tell that the hypotenuse is alpha, and the hypotenuse over here is alpha as well. So we know that we did that part right. We got the value we're looking for, which means the other 2 are also going to be right. That means that the height of our new triangle is √3 alpha over 2. And that's all we need, really. We just need the base. We already have the base, and now we just have, we need the height, and we just found that as well. So the height is going to be square root of 3 times alpha over 2. So hopefully I don't need to bring that back. Hopefully we're done with the picture. I'm pretty sure we are. Now we want to do the same thing with the square. Let me label these first. So the triangle has a base and a height. So actually, you know what? Let's go ahead and find the area of the triangle now. So the area is going to be 1/2 base times height. One-half base, which is alpha, times height, which is square root of 3 alpha over 2. This is our height. And then perimeter, we already know that the perimeter of this particular section, this triangle, is going to have to just be 3 times alpha. All right, now we're going to do the same thing for our square. The square is going to be much easier. we can tell that because the vertical side length right here is beta, we can tell that the other three side lengths are also going to have to be beta. So base and height are both beta. And we can tell that the area of the square is going to be really simple. It's just going to be beta squared. All right, now we have an expression for the area of both of our figures. So now we're ready to get into the optimization. Remember that it involves taking the derivative of some quantity and then using that derivative to find the critical values. And then we can determine whether or not we have a true maximum or a true minimum. But before we can do that, there's a very critical step we have to do. Remember, we always have to put things in terms of just one single variable. This is in Calc 3. We can't really do things in terms of two variables at once. We have no choice but to put things either all in terms of alpha or all in terms of beta. So let's take a minute and think about how that process might work. Oh, and by the way, I invite you to try the problem on your own. I mean, the solution is going to be here if you need it, but I really, really highly recommend you try the problem on your own, see how you do. And if you get a mistake, it's always a really good idea to be in the habit of matching your work with the full solution. That way you can understand what you did wrong. And that way, if you run into a problem like this on a test, you'll remember, oh, I did this wrong last time. I don't want to do that again. So it's a good problem solving strategy to do that. So give it a try. I put the video on pause and come back when you feel like you have a solution. Let's continue. So we're trying to first maximize the combined area of both shapes. So I'm going to use A for area. And then actually, I'm going to go down here. I'm going to do A sub T, which is area of the triangle, and then A sub S, which is area of the square. So just A without the subscript is going to be the total area between both of them. So this is going to be 1/2 alpha, or actually, you know what? Let's just combine everything together. Let's just multiply everything. We're going to get root 3/4 alpha squared. Plus the area of the square, which is just beta squared. So now what we need to do is put things in terms of just one variable. So it doesn't really matter which one you pick. I'm just gonna pick, let's see, I'm gonna put everything in terms of alpha. So I'm gonna take our perimeter equation and I'm gonna solve this for alpha. So before we continue, I wanna replace our identifier P with 10 because we definitely know what that is. We definitely know what the perimeter is. So we can use an actual value instead of a variable. So 10 is the perimeter. 10 is equal to 3 times alpha plus 4 times beta. So now what we want to do is we just want to solve this for beta, because if we solve this for beta, we're going to get beta equals something in terms of alpha. So I'm not going to grind through the tedious busy work. I'm just going to tell you guys that beta is equal to 1/16 times 100 minus 60 times alpha plus 9 times alpha squared. So now that we have that, we can substitute that in for beta. And we want to square this first of all. We have beta. What we really want is beta squared. And again, I'm not going to grind through the tedious busy work. I'm just going to tell you guys what it is. So when we do that, whoops, sorry, made a mistake there. This actually is beta squared. This isn't just beta, this is beta squared. So I'm going to be lazy. I'm going to erase this beta squared. I'm going to replace it, I'm going to replace it with this expression, if I can do it without messing things up too badly. Nice, all right. We're good to go. We have everything in terms of only alpha. So before, we had an area function that took a value of alpha and a value of beta, returned an area. Now what we've done is we've converted it into just one single function of one single variable. We have a function that produces an area based on alpha, based on just one variable, which is great. Makes things really, really easy for us. So remember, now what we have to do is we have to find the critical values. We're going to have to find the derivative of the area with respect to alpha. And I invite you to pause the video right now, take the derivative yourself, and then see if you get the same thing I got for my derivative. So when I did this problem, I got this as the derivative. And by the way, this is simplified. I canceled common factors in the top and the bottom of these fractions, and I got this. I got square root of 3 alpha over 2. Well, meant to make that different. Square root of 3 alpha over 2 plus 1/16 times the derivative of everything inside the parentheses, which would be 18 alpha minus 60. So now what we want to do is we want to find the critical values. We want to set the derivative equal to 0 and then see if we can find those. So what I did is I found a common denominator for everything. I condensed everything into one single fraction to make it easier for us to do what we need to do. So what I did is I got 8 root 3 times alpha plus 18 alpha minus 60. Equals 0. So then I'm going to skip some of the steps for the purpose of time. I got this. I got 4 times square root of 3 alpha plus 9 times alpha equals 30. And this is what I got for my final value of alpha. I got alpha is equal to 10. It's not a 10. I got alpha is equal to 10 times 9 minus 4 square root of 3. All over 11. That is alpha. So if we did this correctly, this would produce what we think would either be the maximum or the minimum. We don't know for sure yet what it'll be, but we also need to find beta. We've only done half of the problem. Actually, realistically, we've done probably less than half, but we need to find beta next. So it's easy now that we know what alpha is. We can easily find beta. So I'm going to take this perimeter equation up at the top, 10 equals 3 times alpha. I'm going to plug alpha in right there. So we're going to get 10 equals 3 times alpha, which is 10 times 9 minus 4 root 3, all over 11, plus 4 times beta. And then just like with alpha, I'm going to spare you the tedious busy work. I'm just going to tell you right away what beta is. So beta is equal to 30 root 3 minus 40 over 11. So we're almost there. We've done what I consider to be probably the most tedious parts of the problem. We found alpha and we found beta. So the tricky part is understanding if this generates a maximum or a minimum or neither. And you just have to have a strong intuition with calculus to be able to determine if it's a minimum or if it's a maximum, or it could possibly be neither. So it's always a really good idea to understand how the process works, determining if this produces the result that we're looking for. So let's see if we can go ahead and find the area. So area, once again, I erased way too much stuff. I apologize for that. Here, get rid of that. So our total combined area is going to be the area of the triangle, which is a sub t, plus area of the circle. No, I almost said circle there, plus the area of the square, which is beta squared. So that means the combined area we know from before is square root of 3 alpha squared over 4. plus beta squared gets us our total combined area. So we can plug in our expression we have down here. We can plug this value in for alpha, and then we can plug the value below it in for beta. And when I did that, I got the following. I got 75 times square root of 3 minus 100 all over 11. This is the total combined area. And once again, that comes from this step right here. It comes from taking this expression for alpha, plugging it in right there, and then taking this expression for beta and plugging that in right here. Evaluate it, simplify it, and then we get this for our total combined area of the triangle and the square. And it isn't that easy to make sense of when it's a fraction like this, especially something like this with an irrational number in it, makes things difficult to work with. So we have, I'm gonna make a decimal equivalent of this as well. So the total combined area in decimal form is approximately 2 72/100ths. So this is the combined area between them. So how the heck do we know if this is a minimum or a maximum though? This is something that trips up a lot of people. So remember that we only found one critical value. And you might be thinking that it's the only one we have, but remember that critical values don't only include the place where we have a zero derivative, they also include endpoints, the left endpoint and the right endpoint on a particular interval. So theoretically, what if we had a triangle with 0 area? And theoretically, what if we had a square with 0 area? What if we made the triangle take up all the material or make the square take up all the material? Let's see if we can find what those areas would be. So I'm going to write case 1. So case 1 would be a situation where we use all the material to make the triangle. We don't have anything left for the square. So the triangle uses up all of our wire in case 1. So we know that we have a total length of 10 meters. That's how much wire we have. And we have a perimeter of the triangle alone of 3 times alpha. So we have perimeter of our triangle is 10. So then alpha would be 10/3. Now we want to find out theoretically what the area of we can't talk today, area of the triangle would be if we have a value for alpha of 10/3. So we want to go back to our special right triangle. So this is 10/3, which means this one at the bottom has to be 10/6. That doesn't seem right. Never mind, that's right. I'm being paranoid for no reason. Bear with me. So then that means our height's gonna have to be, let's see here, that would be, hang on a second, sorry. That would be 10√3/6. So now we can go ahead and find the area of this triangle that takes up all the material. So if we don't leave anything left for the square, if we use all of our wire in making the triangle, we get a triangle area of 25√3/9. And then I want to make that into a decimal as well. So that would be approximately 4.8100ths, 4 and 8100ths. So now we want to do the same thing for the square. So the square is pretty easy. We already have, here, let me erase some of the stuff we don't need anymore. I think I'll keep this because I know if I erase it, I'll suddenly need it again. So just to be on the lookout for that. I'm going to just resize it, move it out of the way, and we'll have enough room to do the rest of the problem. So the square is going to just be beta squared for the area. So A sub S, area of the square, is going to be beta squared. And actually, hang on, let's see if we can find beta first, because remember that beta in this situation is going to be a lot different than beta in this situation we have in the bottom right-hand corner of the screen. This beta right here in blue refers to the critical point where we have wire for the triangle and the square. The beta we're trying to find now would be the value we get when we don't make a triangle at all. We only make a square. We use all of our wire in making the square. So let's see if we can find that real quick. So alpha is just going to be 0 because we're not going to include a triangle in this. We're only including the square, which means beta is going to be 10 over 4. If we reduce that, we get 5/2. So that means the area of the square with the side length of 5/2, we're just going to square that. We're going to get 25/4. All right. Not so bad, doing all right so far. So now what we want to do is we want to do what we did in the other ones. We want to make this into a decimal as well so that we can compare them. So this is going to be, I don't know why I'm putting the little squiggly equal sign. We can use an actual equal sign because 6.25 is the actual value. So, oh, I should have labeled this case 2. I apologize. Case 2, we use all of our wire in constructing the square. So let's compare our results. So for part A, we want to find a way to cut the wire so that the combined areas produce a maximum. So we want to compare case 1 with case 2, and this case we get when we find the critical value between both of them. So we have 2.72 for that. That would be our minimum. And then our maximum would be this case 2, because we're comparing this quantity with this quantity with this quantity. And it's nice to have all the information kind of just laid out for us like this. We can tell that our minimum is going to have to be this value right here. Our maximum is going to have this value right here. So to answer part A properly, using the vocab that we need to use, we would cut it in such a way to produce a maximum such that we have only enough wire to build a square. We're not going to build a triangle at all because technically that is legal. Technically, we can use 0 meters of wire theoretically to make a square. So if we use our wire to only make a square, we get a maximum. So that is our answer for part A. We use no wire in building a triangle. We use it all in building a square. And then for part B, they're asking about producing a minimum. So for part B, we can tell that our minimum value we get is when we make both shapes. We have a triangle and a square with these dimensions. So these two would need to be part of your answer. You would need to have alpha be this fixed value, and you would need to have beta be this fixed value as well in order to produce a minimum.